Hey, everybody. Really quick to kick this off with some quick introductions. I'm Vikram Chatterji. I'm the co-founder and CEO at Galileo, a data quality intelligence platform for machine learning practitioners. We have a great set of people here today who've joined us for this webinar. Really honored and glad to have them here. You can maybe start with quick introductions if you want to go first, Alex.
Sure. I'm Alexandra Levinson. I'm a principal algorithms and AI engineer at Elbit Systems of America. My background is in tracking systems, so I do all types of machine learning models, mostly targeted towards image processing, classification, detection, and tracking systems. So very excited to be here and talk to you too.
Amazing. Andra, do you want to go next?
Absolutely. Hi, my name is Anirudh Kool. I lead a team of which does machine learning data sciences, which means that we look at how machine learning engineers actually train their models across Pinterest, and could we then apply more science on top of the ML itself to make them more productive? So I've been working previously. I used to work at Microsoft Research and a startup. So computer vision is really close to the heart, and I wrote all about my frustrations in a O'Reilly book also. So happy to share my frustrations today in the webinar.
Well, it's great to have both of you. Clearly, both of you have a lot of experience in the world of computer vision and are experts in this field. Something which we wanted to talk about specifically during this webinar is about the criticality of data, because models are getting increasingly commoditized, and people are realizing more and more in the enterprise that data is becoming the moat for them so that they can train with higher quality data. A couple of years ago, there was this term that was coined around data-centric AI. Would love to get your thoughts about, specifically in the world of computer vision, from your experiences. How critical is that for building good computer vision models in industry at scale? And if you have any horror stories to share about when that was not done well, that's also fair game here. Alex, if you want to go first on that.
Sure. So I think that there's been a lot of focus. So my background is more on the algorithm side. I've done some work on the data side as well, but have been more focused on the algorithms. And I think there's been a lot of focus on getting the algorithms perfectly written and a certain level of complexity and tailored for certain purposes. As we have more kind of plug and play algorithm platforms, and it's really becoming more democratized, I think it's important to leverage this wealth amount of data that we have just sitting around, and really sift through that, make sure that's in the proper, formats and giving us what we want, because there's only a certain point that we can get to with the algorithms. If we have bad data, we're going to have bad algorithms. So focusing on both of those, I think, is critical for our field especially.
Yeah, that makes a lot of sense.
I'll add to just the importance of data to what Alex said. So in 2016, there was this study about how long it takes for an algorithmic uh, uh, breakthrough to happen in computer science versus how long it takes for the similar breakthrough to happen since a data set was released. And what they found was that if you go pure algorithmic side, it would take 18 years. Whereas if you had the data set actually built, that would take 3 years. It was like a 6x difference. And if we are looking at all the generative models in the last like 2-3 years, I think those numbers, 3 years sounds like already pretty big. So it kind of showcases that importance of the data. Um, I tell people that if you want to be famous, you can work on uh, a more algorithmic paper. But if you instead publish a dataset paper, you'll get more citations much more quickly and will be much more well known, which is kind of becoming the truth. So people have started moving away from, uh, as you said, these models are becoming a lot more commoditized. So the real difference that you can make is how do you model them with the data set that you have. And data set is also like a motivation to increase the benchmark quality, be more creative on the model side. So it starts more importantly with the data side. And the other thing that has happened is, people have moved away from a pure model centric view to trying to understand things like undesirable flaws in the data, anomalies, missing values. So those all like sort of make that data centric view much more important. And we can talk about horror
Yeah.
stories all day long.
Yeah, I mean, I'm also curious about when it comes to looking into the data, especially as compared to looking into the model hyperparameters. There, it seems like a couple of years ago, when it was more model centric, like you said, um, there were certain patterns around how you can look into the model and tweak the hyperparameters. Versus now, when you're looking into the data, even in the beginning, when you just have a huge corpus of image data, let's say to start out with, what has been your experience in the industry in terms of just seeing how people work with this huge corpus of data to figure out what the right kind of data is to label or to train your models with? It has. Do you feel like it's still an extremely messy process, or is there some semblance of a process emerging here that people in the industry and people listening to the call can actually adopt? Alex, if you want to go first, if you have thoughts on that.
Sure. So my perspective on this might be a little bit different than yours since I'm working in defense. A lot of our data sets, we're not working with big data sets a lot of the time. We're not sifting through large amounts of data. So a lot of it unfortunately, isn't automated. And we're working towards getting more of those ML ops and data ops like pipelines really integrated. But that's certainly a modernization step that we're working on. It hasn't, like I said, it hasn't been a huge issue in the past because we haven't had huge data sets just because of what's available. But, as more simulation capabilities, generative AIs, we have all of that, and we can actually augment our data and stuff. That's going to be something that we're working towards for sure.
Makes sense. I'm always curious about the world of the small data world as well, because what we've noticed with a lot of our financial services customers, healthcare customers, similar to what you said with defense, is that either you don't have a lot of data or you don't have access to a lot of data, even if it is available for actually training your models with. That's also a huge challenge. What would you suggest for people who are in that kind of a world similar to you? Would you use synthetic data instead, or are there techniques which you can leverage around active learning, etc., that with smaller amounts of data?
Yeah, so we're big on using synthetic data for that. We try to do representative data collects. So a lot of the work that I'm doing is eventually going to go on a certain type of UAS or drone, and we'll have like a different type that's our like test bed, and we'll do our data collect that's represented. So there's that aspect, but from the purely data science point, we're big into synthetic data. We have a pretty high fidelity simulations. We use the same simulation engines video games use a lot of the time. So it's a big push for us in the small data world, certainly.
Got it.
Yeah.
Got it. That makes a lot of sense.
I'll add to the simulated data training and inference. I think when you have to scale things up, the value you get with simulating data is just enormous. The danger is where the data scientist would start to look into. So one thing that I had been doing was that have two test sets. One is a test set which is also generated from simulated data, but one which is like hard real world data. To essentially try to find that was there a bias in the way I was collecting with the parameters I had set in my, the way I was synthesizing these images. So keep a real world hard test set, but it would probably be smaller. So that's one part. The second part is also about this is maybe less related to synthetic data, but essentially versioning of data. So your real world data is basically always being collected. Your size is increasing. The quality might be changing when people find issues. They might be. It's not like a one-time done deal. It's always moving. So having a system to version the data and then having templatized scripts to reevaluate your benchmarks as the version changes would be very essential, especially as this moving target is it's always moving.
Yeah.
Yeah,
Yeah,
I
so
agree with
that's
that.
really, yeah, go ahead, Alex.
I was just saying, I agree with that, especially for us, we do a lot of different data collects on different sensor types. So that becomes especially into play with versioning and making sure, we're getting what we think we're getting.
Makes a lot of sense. And in terms of just using these scripts, like you said, around trying to find out different kinds of data quality errors, are there specific kinds of data quality issues or errors in the data that folks should be looking out for when while they're training their models, or even before when they're trying to figure out what data to work with? It could be even on the synthetic data side. From our experience working with companies who are dealing with synthetic data, the question becomes what kind of data should be synthesized in the first place. But
Mhm.
are there specific things that people should be looking out for when they're trying to figure out what these scripts should be, and what their goals should be? Because when it comes to data quality, the number of things you could be looking out for could be enormous.
So coming from the side where the data is often data that's coming from like image data and other sensors that are like IMUs and those types of devices, a lot of the quality concerns should be on the repeatability and the consistency of the data. So things like making sure you have the right amount of pixels, like rows and columns in your frames that are coming out, and the frame numbers are consistent, and you're not getting frozen frames, and the timestamps are increasing. And there's a lot of little things in the metadata that could really mess you up if it's not consistent. So
Yeah,
a lot of that is doing those checks and making sure we have like proper repeatability tests and those types of things.
I
makes
would
sense.
I would put a plugin for something software engineers have been doing for decades, but data scientists don't, which is similar to unit tests but for data. So while the data is coming in, uh, having some sort of a test on the data distribution that is being collected, which will eventually be going to become training data,
Yeah.
uh, as well as changes in the test data. I think those would be really essential in the long term. Set up alerts, maybe train like a small proxy model which just does has the main base model, but just trained a little bit to see if the metrics change by a lot. Are your
Mm.
probability scores changing by a number more than normal? So those would be the kind of things that I would encourage uh, for the real world version.
Yeah. In terms of this robustness of process, like having these unit tests or looking into the metadata, like you said, Alex, like are you seeing this becoming more and more common in the world of data science, let's say compared to 2 or 3 years ago? Is it what direction is this moving in? Is it is the process getting commoditized as well, or are we very far away from that right now?
I think it's becoming more and more standard practice to be doing the continual integration, continual evaluation of data in your pipeline, especially as it becomes easy to set it up. You can
Mm.
do that, connect it to GitLab and have that working automatically in the background. So we can actually make machine learning models to evaluate the quality of our data as long as the data going into those models is adequate and
Yeah.
automatically detect anomalies and things like that in the data.
Yeah, I think if I look at the venture capital landscape, I think this has especially been the top of mind in the last 3 years ish. On like they are recognizing. I think if you looked at like over time, it's like, hey, you make an amazing product with AI.
Mm.
Either you open a data labeling company, and now I think data labeling companies itself don't get the venture dollars. It's like who can solve for the issues underlying in the data. I think that has become a main topic, a main theme, um, because of its importance.
Yeah. Yeah, makes sense. And to that point, actually, like with supervised ML, if you just take that workflow where you have humans in the loop and labelers in the loop, which is still seems like fairly common in industry. Uh, have you seen there, if you look at the ML workflow, let's say break it out into three parts, the data prep before you even start labeling, you label your models and now you're training and iterating constantly on it. And then now you're the third one being your models in production. Would love to get your thoughts on all three pieces there. Like, what would you suggest for people listening in for how they can be better about managing their data on all three pieces there, and any kind of gotchas that they should keep in mind while working with this kind of a supervised ML workflow from a data perspective?
Yeah, so I think, like I was kind of mentioning before, I think that going through, like ahead of the time, going through your data and making sure it's what you expect when you're feeding it into your model is so important. It should probably goes without saying, but garbage in, garbage out. That's still true with machine learning. So yeah, whatever process is, obviously if that can be automated, that's ideal. If you have your engineers looking through that smaller data, that's more reasonable. And then having those pipelines where you can detect anomalous data when it's going into your models for the continual training. And yeah, having that whole process kind of be supervised and not too much attention or a lack of attention be put into one of those specific categories, I think is something that we all need to focus on. But definitely going into it, having that data be the proper format, and what you want representative. It's also really important for making sure that you're not introducing things like biases and all of that. So,
Yeah, I would, to add to that, I would look at a really important, something really important is basically the ability to understand the data you have, the ability to visualize it and both summarize it, maybe cluster it, to be able to dig deep into what kind of data you have. And, if the data scale is large, there are bound to be issues of some kind in there. Um, and essentially to try to understand where those areas are, that will, an ML model would have a much harder time learning. So I think that depth of understanding of the data at scale becomes harder and harder, especially as the definition of scales goes from like 60,000 things to millions and millions of items. I think I already talked about the versioning and the reproducibility of your tests. I will say one part, which is when you look at academic um academic understanding in the academic world, you have a data set to begin, single data set, and you work on it. Whereas people who are working in the industry have to go through that constant flow again and again. And there is still a lack of, even there's still platforms which are not like, people try to do it themselves by like making one thing using active learning another thing, and they are trying to do it themselves one by one. Whereas I think having like a one single system to help in that storyline would definitely be quite helpful. Um, those are some ideas that come to mind.
Yeah, it makes a lot of sense. And the point about like biases, especially that you've mentioned, this comes up all the time with a lot of our customers here at Galileo. Like, how do you identify this, especially when it comes to high stakes machine learning models in healthcare, financial services, sure, in defense as well. Like, you can't go wrong, and your models have to be high performing at all points in time. I guess I have two questions that I'll start with the first one. Like, how do you detect these biases, and how can people be better about this? Because right now it feels like it's a little bit of a like a guerrilla warfare with your data is what's going on right now. But how can people be a little bit more systematic and better about detecting these kinds of biases?
So I think a lot of it is knowing what you're putting into your models, going into it with that. So we have like certain models that will do detection for certain types of objects. So we want enough of the relevant objects. We want enough, of everything else. We want enough of the in between. We want it to actually, identify this in the likelihood that we think it will be present, like will be ingesting that type of data, I guess.
Right.
Yeah, if you have like an expected baseline, also this comes into simulation data as well. It's easier to maybe, if you have so much control of the scenario, it makes it a little bit easier to prevent injecting biases in there. And you can use a simulation as kind of a baseline and assess the real world performance against that. And if you see deviation, then that's something that you can look at for sure.
Makes sense.
So often what you can do is, I think finding biases in the, what do you call as, I won't call it a dark arts, but basically it's like, the more you are aware of the kinds of biases there are, the more you are actively thinking. So the more we talk, the better it gets for the whole community. I will say, so, one way is like you have the data set and you start with just analyzing, hey, are there certain classes which are, underrepresented? Uh, but then you start digging down into like, there must be like multiple different dimensions or different sets of features where, for example, even just like if you're a self-driving car, it's raining in the evening versus it's raining in the afternoon. Is there like a difference in that sort of like just learning amount of data we have? Then the other is you can actually go not at the data set, but how the data set was itself collected. I remember there were some studies done on, I think, recognizing diabetic retinopathy done by Google. And they found that they were able to recognize if it's, I forget, is the male versus female or their age or something, but eventually they realized they were able to recognize the microscope they were learning from, because there was something left on the images that could enable them to learn the actual data instead of learning from like the images purely in itself. So I think we need to both look at the data and how the data was collected. Yeah.
Yeah, it makes a lot of sense. And I guess the second part of that is like you both touched upon how it comes down to the data sources, the distribution of data, and kind of inspecting that at all points in time. Let's say a model is in production. Are there any suggestions that you would have for when a model is in production? How, when you're constantly trying to retrain the model, how do you figure out what data you should be retraining your model with? And now I'm glad that both of you come from opposite sides of the spectrum, because Anirudh, it sounds like at Pinterest you probably have a huge corpus of data to maybe choose from, versus Alex, on your side, it seems like it's synthetic data that you can generate. But how do you figure out what data to select next for retraining a model?
Yeah, so that's always kind of difficult. You have to trade off between making it super generalizable and designing too much for the current mission. For us, like I said, we have different sensor types, we have different target types, we have different platforms that they're going to be on. So we need it first to be representative of all of that. And that kind of narrows it down to a relatively small data set. Once we have that data set, it's up to the engineers, and I like to think that we have good enough engineers that are cognizant of this stuff, to not overrepresent one class of target type, or whatever you're looking for, and to make sure that there's a good spread of just representative data that's coming from the right sensors, the right platform. Yeah.
Just a quick follow-up on that. Is it typically very manual, the process to inspect the data and to try to figure out if there's a representation and the class distribution, for instance, is actually good? Or is that also something which is automatable and is automated already, let's say, when you're working with trying to figure out what data to train with next?
I think we're at that transition point. So a lot of it still is manual, but in the last few years, I've seen significant growth just in the defense field in general with getting things automated and streamlining that process. So hopefully if we meet up and talk again, I can say that everything is all automated and streamlined.
Yeah, move in that direction. Makes sense.
Yeah.
Anirudh, any thoughts on that?
So if you look at it, always is a question of how and what scale you are operating on. So if you would look at most consumer internet companies where the scale is quite large, the number of API calls is like, think of it like in millions per second when you're talking at those kind of scales based on the usage from consumers. One strategy is that you just sample data from how the consumer internet is behaving. And based on that sampling, you add that to your, like the delta to the iterative training set. You train that model, but here is where like you don't release the model. What you do is you actually set it up for an A/B test. So every release ends up being an A/B test to actually see that, hey, does this change our metrics by too much? So as a part, and there are actually other metrics that you're not optimizing for, which could be negatively impacted. So having that as the way to test would be the way to go. So yeah, that's the when you don't have data sets like which you can actually maintain just because the scale is too large. I think having that A/B testing is the way to go.
Makes a lot of sense. I guess shifting gears a little bit, and there's been a huge buzz around generative AI now, and I guess like these models that were around for a while, and now they're getting a lot of attention and a lot of more application in industry across large language models, but also across like image-based models. What's your take on the future of this data-centric AI concept that we've been talking about? But how does that lend itself to the world of generative AI, as you see more and more applications in this field coming up?
Yeah, I think there are huge benefits to generative AI and creating synthetic data, especially. We can use generative AI to simulate things like scenarios on different sensor types and get data for a specific sensor and platform configuration, even given a specific trajectory. So you really can just write in the inputs and can get really representative data from generative AI, and that will help us pretty significantly cut down, simulation time, make sure that we have all of those representative data sets. I think there's huge potential there.
Gotcha.
Yeah.
Anirudh, any thoughts on that?
Yeah, the value is obviously large. The scale of data that's being used is also getting larger. So if you look at papers in 21, 22, one item was clear. I think models are increasing in size, but even if you keep the model of the same size, the value of the diversity of data used to train these models is actually triumphing. So today you have models like Llama, and now you have Vacuna, which is claimed to be 90% close enough to GPT-4 right now, which is the current evaluation metric that they have. But it's the data set and the size of the data set that's actually going to dictate. So even if you have a model which can fit in a single GPU, but you just had a lot more data, you would still get that benefit. Now, from that comes the real problem of working with these data sets. So when DALI 2 came out, there was an active effort to understand the data set behind it, to be then able to do diagnosis on what things we don't want in the training data set for a generative AI system. So one of those examples was, uh, hey, we got this as the generated output, but what was the reason for the data set behind it? So originally it was more for like cleaning up and keeping data more trustworthy and, safer work.
Mhm.
But then they found like, hey, we scraped the internet and we found different clocks, and these clocks were actually just vector arts, and they were in vector arts. What was happening was that people would make the same clock and just change the number or the thing around, like how the clock goes, but it's
Yeah.
exactly the same clock. And now what's happening is the bias is around the same view of the clock appearing multiple times throughout the thing, and that's what it was learning a lot more on, given that there are
Right.
100 minutes in a day for the clock and
Yeah.
hand to. So that's why deduplicating the data set, understanding where their opportunities are at improving at that large scale becomes important. And one of the ways people do it is like building actual search systems and similarity understanding systems to be able to cluster the data and find those unique facts and then decide what to do.
Mm-hmm. It makes a lot of sense. And it's going to be really interesting to see how this grows in the industry when people start using these generative AI models for enterprise applications on their own use cases, and that kind of fine tuning the model a little bit for their own use cases. I'm sure we'll see a lot more interesting use cases and also some horror stories perhaps coming out of this, but we'll all learn from that.
I'm actually going to add to the horror stories part that Neuro IPS has a data set and benchmarks track. And one of the papers in 2021 was essentially just going over all the computer vision data sets and finding that some data sets, like the revered data sets from MNIST to CIFAR 10 to the Google Quick Draw, have like on average like about 4% error rate. Something like CIFAR 100 has like 6% error rate. Google's Quick Draw has 10% error rate. Now imagine things that we literally publish our benchmarks on have that kind of error. Our numbers are like all
Yeah.
incorrect. But the most interesting thing that was noted was that if these data sets had just uh, larger models like ResNet 50 would under smaller models like ResNet 18 would outperform the larger models like ResNet 50 if the error was fixed. The point is that
Mm.
these large models are actually overtraining on the noise in the data set. And because of that learning on the noise on the data set, they are able to perform great on a normal benchmark. But if you fix it, a normal ResNet 18 was still capable enough of doing well. Just
Mm.
that fact is scary enough for like
Yeah.
not going model centric, but fixing that error in the data.
Yeah, it's a great point. I know we're almost at time, but any final thoughts from either of you on this topic of data-centric ML and where it's going in the future of computer vision?
Yeah, I think that just think there's a huge amount of potential to expand what we're capable of. Going from, I mean, just 5 years ago, the state of the art in defense was using the old school signal processing methods, and now we're
Yeah.
moving towards having machine learning and having the right data, synthetic data, and it just opens up a whole world of capabilities for us.
Yeah.
I like the world of like everything evolves over time, and we take the best, l- learn from the bad stories to make it like a best practice of never having to repeat again, templatizing those approaches as a process, and it's like it's an understood expectation instead of like rediscovering them again. So
Yeah.
I like where this is going.
Absolutely. And I'm so glad that we are discussing this. Hopefully, there are many other such discussions that happen But thank you so much for your time, both of you, Alex and Anirudh. This is super, super helpful, and hopefully, this is going to be helpful for all the people who are listening in as well. Thank you so much again.
Thank you.
Thank you.
Great. Well, after that really great panel discussion with Alex and Anirudh, something which we kept hearing over and over again was how there is this garbage in problem, right, in data science, and uh, the question about like, how do you make sure that you're working with the right kind of data, and also being on top of the fact of what data is putting the model performance down becomes really important. So in this quick demo, what I wanted to show you was how you can be better about managing your data and making sure that you can find the data that is hurting your model very quickly. In my past experience, it's been a very manual and painstaking process, and that's what we were hearing from Alex and Anirudh as well. Rummaging through the data and looking into it and figuring out what images are pulling the model performance down, in what way, what the errors are. It's very hard. Um, and having worked with many data scientists in my past, I can very much empathize. So let's see how you can use Galileo, and you can very quickly look at the data, find out what the error patterns are, and then also fix them all in one place. So let's quickly jump into that. So to start out with, how do you start to use Galileo? It's very easy. Once you sign up for free on the website, as you start training your model, which in this case, as I'm sharing on my screen, we're building a model where we're using ResNet 50. I'm also using a public data set, which is this data set called Food 101 for an image classification use case. In this notebook, as a data scientist, I'm just literally just training my model as I always would. The only difference that I have to make as I use Galileo is to number one, install our data quality client, which is essentially the Galileo SDK. It's called data quality because that's what we do. And once you do that, you log in, you give your project a name. In this case, I'm going to call it Food 101 Image Classification. Within that project, you're probably going to do many, many different runs, right, as you're trying to improve your overall accuracy scores. For this, I'm going to name the run ResNet 50 based on the model that I'm using. And that's it. I just add a few lines of code just to watch the model, which is essentially allowing Galileo to log all of the data that the model is training on, as well as the model metrics as it's converging on specific labels behind the scenes. And all of this is used to power Galileo's data-centric algorithms so that we can show you the alerts immediately in the UI. And that's it. You just add one line in the end for DQ called DQ.finish, and you get a link to the Galileo dashboard with all of the errors right after this. So when I click on that link, it takes me to the dashboard, which looks like this. You can see here that it's there's the project name, and then there's a run name at the top. There's a bunch of different kinds of alerts that surface on the left-hand side. And this is really important because these are all processed automatically by Galileo, and they surface over here. They're powered by a lot of the algorithms that have been built out already. And on the right-hand side, you have all of the images that you've trained with for this image classification use case. So you have your ground truth data for each image, the predicted label for each image, as well as what we call the DEP score. Now, I'll get into this a little bit more in a bit, but high level, think of the DEP, or the data error potential score, as a score for how hard was it for your model to train on that particular image, right? And we're looking at how difficult was it to converge on a specific label. And this is a very powerful metric. And think of this as a huge replacement for scores like your confidence score, to tell you what the long tail of data quality issues are in your entire data set. In this case, it's a 30,000 image data set which is a publicly available data set that we used just to see what kind of issues we can find here. And immediately we could see that there are a whole host of problems that Galileo surfaces, right? Like you have about 3% of your data are likely mislabeled. So the ground truth is most likely wrong here, and we can automatically detect that. There's 20% of your data is hard for the model, which means that there's a very high data error potential score. We automatically figure out what the right thresholds are based on the data distribution. There are 24% misclassified samples, as well as when you have a lot of different labels, you can have a lot of different kinds of low-performing classes as well. So that shows up, as well as looking at how much class overlap you have. So it seems like in this case, you can see that there's a huge amount of class overlap between labels such as filet mignon or foie gras, baby back ribs, pork chop. So as you would imagine, like when you look at these images, they can sometimes seem and look very similar. So obviously the model is getting confused between these similar kinds of foods, and Galileo has scores to automatically detect the amount of overlap as well as the specific data that it's overlapping on. So now what we'll do is just go through a few of these one by one just to see what we can do about this, because identifying and detecting these kinds of errors is only one side of the coin. You actually have to fix it right after that, right? So what I'm going to do here is let's start with likely mislabeled samples. When I click on this, I can see that it's starting to show me a whole host of different metrics here. So the F1 score is obviously really low. It's 0 for these likely mislabeled samples. It's a total of around 900 data points, which is about 3% of all of my data, which is a fairly significant amount in this public data set to be mislabeled. Let's inspect a few. So let's click on the first one here. It literally says macaroons in the image, right? But the ground truth labeler said it's a red velvet cake, which is obviously mislabeled. Now the model got this right, but it's a mislabeled data set, so data point. So you might want to fix that. If you go to the next image over here, so I can pick up this one because it's a little bit more clear. The human labeler said it's a grilled cheese sandwich, whereas it's clearly a hamburger, and so on and so forth with all of these different foods. So if you're a food connoisseur, then you can probably check and see that a lot of these are indeed mislabeled. We can also, in this case, I don't have a very big labeling budget, so I want to be absolutely sure if something is mislabeled. So I can tweak the algorithm to bias more towards a high amount of precision here. And when I do that, I can see that the data set size reduces to 243, but it's highly precise about the samples that are mislabeled here. Now, as a data scientist, I would have otherwise had to spend many hours and days in just trying to figure out what the mislabeled samples are. But here I could just get this within a click of a button. But now I can select these, and essentially I want to send this back to my labeling team so that they can relabel this. Or I might want to just change the label directly within Galileo, and a whole host of different actions show up as soon as I select images. I can find similar samples to this from my training split or my test split, or even from my production data split. That's also available. I could just export this data, remove this data, change the label directly here in bulk if I wanted to. Or in this case, I'm just going to send this for relabeling, which happens through our integrations with all the popular labeling tools out there. In this case, I'm going to hit send for relabeling and going to create a project for this. I'm using Label Studio in this case, which is a great open source labeling platform. And I'm just going to create a project here. And once I do that, I just hit send. So I'm going to create a sample, say these are mislabeled samples for relabeling. And that's it. When I hit send, it goes in for relabeling. And I'm not going to do that here. And as you can see, I just closed that because I don't want to create a new project in this case. But you could easily do that and create a new project for relabeling and go on with your workflows from there on. So it's really fast to be able to identify the data that you want to relabel and then go to the next step. That's just one of many things you could do here. I did talk a little bit about the DEP, or the data error potential score, earlier. So let's analyze that a little bit more. I'm going to close this this alert, go into my metrics tab here, and I can see here that I can look at a whole host of different kinds of metrics, including my F1 score distribution across all of the different classes, the sample distribution count across all of my classes, as well as this DEP distribution. So this is my distribution of the data error potential score. Think of this as automatically identifying what was hard for the model, which is all of these data points which are marked by a red here. Seems like there are quite a few that are hard for my model, as well as what is easy for my model, which is the ones which are green over here. In this case, I'm just going to mark the ones which are hard for my model and very quickly identify the ones which my model is having a difficult time with. I can also look at my fine-tuned embeddings here. When I look at the embeddings, and mind you, these are your model's embeddings, I can color by the data error potential score to quickly get a sense for what was truly hard for the model. I can even tweak this further and make this even more precise so that I can get a sense for specifically what was very hard. And now you can see almost like an X-ray view of the data to identify what was difficult for the model and zoom in and try to identify what the model was having a difficult time with. And clearly here, while I inspect this, I can see that it's getting confused between ice cream and frozen yogurt, which is very fairly understandable. So maybe I might want to take some action on that if I wanted to. So you can quickly select the data that is having a hard time with over here, and start to look into that even further and inspect it and start to take some action here further. So what you can see here is Galileo allows you to very quickly, with a few lines of code in your notebook, it's not just inspect and visualize your data, that's the easy part, but actually figure out what the different kinds of data errors are, inspect them very quickly, and then also take action on it, and further be able to manage all of these projects and runs all in one place and compare them over time to make sure that you're actually working towards a very high performing model. And if you find that you've worked with a better data set in the past, you can easily go back to that very, very easily. So you can manage your data sets, manage your model, manage your projects and runs while trying to fix your data sets in this one singular data intelligence platform. All of this was just for image classification. If you are a practitioner that works on, let's say, object detection, it's again very similar, where in this case, we used the popular COCO data set. And again, you can see how the same errors and the same algorithms work very well here as well. So you can start to get to see a whole host of different kinds of error patterns here around, what your mislabeled samples are, etc. But also things like when you have background errors or missed boxes, etc., which are essentially, as one example, the background errors use case is one where you can very quickly see what the ground truth labeler completely missed in the past, but the model actually captured that background error very, very easily. As an example over here, these are images of orange beetles, but which the model seems to have gotten and predicted, but the ground truth labeler completely missed. And being able to get all of this with one click allows you to be able to select them and again send them back for relabeling, so that in the future you have a better annotated data set to train on. So these are some really quick ways of how you can leverage Galileo to be able to get to a better performing model much, much faster, for whether you're using image classification, object detection in this case, or even semantic segmentation at the pixel level. So if you like what you see here, please go to Galileo and it's rungalileo.io, sign up for free, go to use it, or get in touch with us. Me or one of our data science team members will be more than happy to walk you through the platform and better understand your use cases. Hope you enjoyed this, and happy building, and please always remember to focus on the data if you want to build better models. Thank you.